All right. With today's lecture, we are going to finish up with one last topic on sintering, and then we are going to jump into our last topic for the semester, which is optical properties. There's a lot of other chapters in the back end of our textbook that we aren't going to be able to get to. A lot of other ones that talk about, you know, the electronic properties, the magnetic properties. So I encourage you, if you are interested in those subjects, to look at them. But we're only going to sort of pick one. And since we've already talked about some optical properties, I'm going to choose that. Okay, so for the last part I wanted to talk about related to sintering, I wanted to mention a little bit about hot pressing. And this is also going to tie back in with forming and shaping techniques that we talked about as well. And so before we do that, we've talked a little bit about this topic of hot pressing. So I want you to think about how you think this compressive force that we have during hot pressing can enhance sintering. Again, there's clearly advantages here, or there wouldn't be this topic of hot pressing. So tell me what you think in terms of what's the enhancement because of this compressive force. So pause the video, see if you can answer this question, and come back and we'll talk about this a little bit more. Okay, so now let's look at why this enhances sintering. And so for this, I bring your attention back to this list of different mass transport mechanisms that we saw for sintering. I apologize for the numbering, it should be numbered, but it doesn't really matter for this case. So hot pressing, and like all sintering techniques, if we're trying to get something theoretically dense, we want to remove porosity. And the way we do that in this case, and the way we aid densification, is through this last form of mass transport that we hadn't talked about up to this point, and that is plastic flow. So with hot pressing, we are from that term, we're at a relatively high temperature and we're pressing, so we're applying a compressive force. So with that, at these higher temperatures, we've thermally activated dislocation motion, right? So, and for the most part, when we talked about the mechanical properties of ceramics, we disregarded this phenomenon because we were talking about low temperature. But here, we've increased the temperature enough so that we can talk about plastic flow. And that plastic flow is the mass transport mechanism responsible for this enhancement. Okay, so let's look at hot pressing a little bit more. And there's obviously, as you might imagine, there's multiple variations of hot pressing. There's hot uniaxial pressing. So this is very similar to what we did in the lab and what you kind of see here. So basically, all this is a hydraulic press. So basically, this is our material in here, and then we're applying compressive stress in what looks more or less like a Instron mechanical testing frame. And the reason we have all this other stuff is that we basically have encapsulated this hydraulic press with a furnace. So we basically add a furnace to a hydraulic press and we get hot pressing. And we're doing this, the advantages of it, again, like liquids phase sintering, it's more rapid and it can result in a rarely fine microstructure. So the particles don't grow as much as they do in other mechanisms. But because of this setup that you're kind of seeing here, it's not trivial to combine a isostatic press, a hydraulic press with a furnace, because the dies that we use and the tooling that we use have to be designed for these high temperatures and different environments. So here, this is a graphite die, and when we talked about heating elements, we mentioned what can happen to graphite and how it can't be mixed with certain materials or it will reduce them. And so there's lots of limitations. And also, if you think about it from a processing point of view, this is not going to lead naturally to a continuous process. And so all of those things would raise the cost of something that has to be hot pressed. But let's look at, again, the advantages here. So this is cesium iodide that is that is hot pressed at 103 megapascals. So this is basically within the realm that we did in the lab, and it's done at 100 degrees Celsius. So typically, another advantage of hot pressing is that the sintering temperatures go down from what the normal solid state sintering would be. So this is 100. So chances are, if you tried to make cesium iodide a conventional way, you would probably have to go well above 100 degrees Celsius for that to occur. So that's another advantage that I didn't really bring up too much here, but that's important to note, is that these temperatures can be greatly reduced because we're applying this compressive stress, which aids in the rapid densification. So this kind of shows that after 5 minutes of pressing this material, we already have a pore-free material. So there's very little porosity. And so hot pressing is frequently used when we want something that's basically crystal clear, translucent materials, because we don't have any of those defects in that material. So we can, in 5 minutes, we're basically done sintering the cesium iodide, right? If all we want is a very fine structure, which can aid in toughness and strength. And so after that, all we get is grain growth. So this is, for the most part, typically not desired, but there are some applications. So for example, these very large grains are probably better for the translucency of this material. And so this might be a very translucent or transparent materials, excuse me. And so for the most part, this isn't going to help with strength or toughness, but there are some optical advantages to doing this. So hot pressing really gives us a lot of advantages. Rapid, it's very rapid. We can reduce the temperatures required, all because we're utilizing this dislocation flow, right? This plastic flow, where dislocations can transport materials now, and they do that very quickly under these applied stresses. And so that's kind of our driving force, is that dislocation motion.